So let us discuss this example of norm. Okay, so see, we have a set x. X means a set of all sequences, okay, real sequences, and which are converging to 0. For example, you can consider this sequence x 1 by n. Okay, you are familiar with this sequence 1 by n. Terms are 1, 1 by 2, 1 by 3, 1 by 4. Obviously, okay, actually infinite terms are there. Obviously, this sequence is converging to 0. So that's why we can say it is a member of x, capital X. Okay, and they have defined norm. Okay, they have defined this norm in this way: supremum of mod xn. So that means, what is it? Supremum value is 1. So that's why norm 1 by n is equal to 1. So in this way they have defined that function norm. Getting? And we have to prove that it is a norm. That means it should satisfy how many conditions? 4 conditions, right? So let us start to prove all conditions one by one. See, just a minute, I will remove this part. Okay, so what will I do? I will take let I am taking some xn be a sequence, okay, which belongs to capital X. Okay, so obviously xn converges to 0 by definition of capital X. Clearly, if you take mod xn is greater than or equal to 0 for all natural numbers. Okay, this is a real sequence. Getting? This is a real sequence. If you take mod, obviously it is greater than or equal to 0, since mod cannot be negative. So implies, if each of them is greater than or equal to 0, so if you take their supremum, obviously it is greater than or equal to 0. So that's why this is supremum of mod xn, n belongs to set of natural number that is also greater than or equal to 0. And this is definition of what? This is definition of norm x, which is greater than or equal to 0. So xn means x, here xn means x, we denote it by x is equal to xn. Okay, this is a sequence. So, and this is true for all x belongs to capital X, right? So therefore in this way that norm satisfies its first condition. Let us go for second condition. Do you know what is second condition? Can you tell me what is second condition? Second condition is norm x is equal to 0 if and only if x is equal to 0, right? So let us start with, so consider, see what will I consider? Consider norm x is equal to 0. I'm considering with it is equal to 0, and finally we have to prove x is also equal to 0, right? So if and only if. So let us go with definition. What is definition of norm x? I will write this is supremum of mod xn, n belongs to set of natural number that is also equal to 0. So if supremum means maximum is 0, that means each term should be 0. Getting? And none of them can be negative, no? That's why. So that's why supremum is 0. That means each of them mod xn is 0, and this is true for all n belongs to set of natural number. Okay, for all elements it is 0. We are having mod 0. Tell me which number having mod 0? So number should be 0, then only its mod will be 0. So therefore I can write if and only if xn is equal to 0, mod xn 0, that means xn is equal to 0, and this is true for all natural numbers. So see, do you know any sequence having all terms 0? That means see, our x is a sequence, no? Basically x is a sequence. So that means x1, x2, x3, this is we have a sequence, but here we are saying each of them is 0, 0, 0, 0, 0, each of them is 0, that means sequence should be 0. So therefore x is equal to 0, right? We started with norm x is equal to 0 and we got x is equal to 0. So norm satisfies second condition also. So let us go for the third condition. What is the third condition? Will you tell me? So third condition is, for third condition we require some alpha constant belongs to R, and x is xn, which is member of x. Okay, so you remember the third condition. So in third condition what we do? We consider norm alpha x, and finally what we want, in at the end alpha should come outside with a mod. Okay, so let us start to do. So this is equal to yeah, so this norm alpha x means xn actually. Getting? So here we will have x1, x2 and so on. So I hope all of you are getting my point. So we will have alpha xn. Okay, alpha xn. So if you consider think about a sequence, so that means we have to multiply each term by alpha. So if you apply the definition, it is supremum of mod alpha xn, right? N belongs to set of natural number, right? But see, if there is multiplication, as you know, if there is multiplication, we can easily take separate mod. So therefore this is mod alpha and mod xn. Okay, but see, here we are taking their supremum, and a mod alpha is a constant and which is independent on n, so that's why we can take it common and you can take it outside. So this is equal to mod alpha and supremum of mod xn, n belongs to set of natural numbers. So this is equal to mod alpha. This is definition of what? Norm x. Definition of norm x. So we started with norm alpha x and finally we could take mod alpha outside and norm x we have got. So therefore our norm satisfies third condition also. So simply we have to prove the fourth condition, but before that you have to make a screenshot of it, and after that we'll go for a last condition. Okay, so let us discuss last condition. In last condition we require two elements, right? So for x means our xn and y means a sequence yn which are members of x. So I will start with, you remember the last condition, we start with norm x plus y, and finally what we should get, if you take separate norm, value will get increase. So see, equality also possible. So this is equal to norm. First of all, I will go slowly. We will discuss each and I will write each and every step, and after that we'll go further. So x means what? X means a sequence x1, x2 and so on, xn and infinite terms are there. Plus y means what? Y means again a sequence y1, y2, right? And yn and so on. So you know well, okay, you know well how to add these two sequences. So that means if you add, so we will have x1 plus y1, right? x2 plus y2 and so on, xn plus yn, and it will be continued there, right? So this is equal to, okay. So now if you apply the definition, what will you have? If you apply the definition, says we have to take a supremum. So supremum of mod xn plus y, since in each component or each term is xi plus y, in that form we have. So this is xn plus y, n belongs to set of natural number. See, supremum, okay, so it will have some supremum. I will call it as mod xp plus yp. I don't know what is its supremum. I am just calling for, I will mention here, for some p belongs to set of natural number. Now I will tell you why it is possible. Because by definition says, if any sequence is a member of this family, it converges to 0. So because xn converges to 0 and yn also converges to 0. Definition says, since these are two elements of x, so obviously both of them are converging to 0. So therefore xn plus yn, this sequence is converges to 0 plus 0. That means 0. So this is a convergent sequence. So therefore I can say, therefore xn plus yn is convergent sequence. And you know that every convergent sequence is bounded. So therefore xn plus yn in FYBS we have seen, okay, is bounded sequence. Okay, it is a bounded sequence, and if it is a bounded sequence, that's why supremum exists. That's why I could write supremum. It has some supremum, we can definitely declare, right, since it is a bounded sequence. Okay, so see, so yeah, this is less than or equal. Okay, what can I write here? Yeah, so if I take separate mod xp plus mod yp, since if you take separate mod, value will get increased. So obviously xp is less than or equal to supremum of mod xn, right? N belongs to set of natural number, and plus supremum of mod yn, n belongs to set of natural number. Okay, so the first one is obviously less than or equal to its supremum. Maybe it will be its supremum, I don't know, but it will be definitely less than or equal to its supremum, and yp is also less than or equal to supremum of mod yn. So this is nothing but norm x, right? Definition says, and this is nothing but norm y. So therefore we started with norm x plus y. I think somewhere we have got inequality here, less than or equal to norm x plus norm y, and this is true for all x y belongs to x, right? So in this way our norm satisfies all four properties. So therefore we can declare, so therefore Therefore, we can declare norm is a norm on X since it satisfies all properties. Make a screenshot of it and after that we will stop. Thank you. Bye bye.